All right, welcome to exoplanets1 session for the afternoon. So we'll start with an invited talk by Jennifer Yi from Harvard CFA.
Okay, thank you. I'd like to thank the conference organizers for inviting me to give this talk and also for supporting remote participation. The first microlensing exoplanet was discovered in 2004, and it was a very massive giant planet. And over the next few years, planet detections trickled in a few at a time, 1 or 2 per year. And this is what the situation looked like in 2008 when WFIRST mission was first conceived, right? At this point, there's only 8 known exoplanets. They're all at separations of about 1 to 10 AU. The majority of them are giant planets. And then they tend to be found around lower mass host stars, and that's the color coding in this figure. And so at the time that this mission was conceived, it was obvious that if planet detections continued from the ground at a rate of only 1 or 2 per year, that simply detecting more exoplanets from a space-based mission would be a massive improvement. However, 15, 16 years has passed since then, and during that time, the microlensing landscape has radically changed. We continue to get planet detections trickling in, but in 2010, OGLE commissioned the OGLE 4 project, which was one of the next generation microlensing projects, and we start to see the number of detections increase to several per year. And then we hit another transition point in 2015. So in 2015, there were over 30 known microlensing exoplanets, and they're found around a variety of host stars. And that was the year that the KMT-NET project was commissioned. So this project is the Korea Microlensing Telescope Network, and it was the brainchild of Chang Ho Han in South Korea. And the goal of this project was primarily to detect the smallest exoplanets. And so in microlensing, the key thing is that the timescale of the microlensing event, or the planet perturbation, is proportional to the size of the Einstein ring, which is proportional to the square root of the mass of the object. And so for an Earth mass planet orbiting in the bulge, then the size of the Einstein ring is about 0.6 microarcseconds, and the resulting planetary perturbation would typically be about 1 hour long. And so in order to actually push to these very small planets, you need observations from more than one observatory on the ground, because if you can only observe for 8 hours of the night, you're missing 2/3 of the planet population. And so that was the first major innovation that Han made in designing his microlensing project, which is to have telescopes at CTIO in Chile, at SAAO in South Africa, and also at SSO in Australia. And between these 3 sites, we can obtain continuous observations of the galactic bulge over a period of 24 hours, and weather permitting, therefore capture all signals from planets, even if they're very short. In addition, this project has a very large camera. It is 2 degrees on a side, and that means that there's a lot more stars that get observed. You can observe the full area of the galactic bulge much faster, and that enables you to get very high cadence over a wide field and to detect the smallest planets. So this is a picture of the fields for the KMT-NET survey. This survey field survey strategy was started in 2016. That's when we started to take regular observations. And in the center, there are 3 purple fields. Actually, technically, these are 6 fields that are slightly offset, but I think of them as 3 fields because it's 2 fields that overlap slightly. And in between the 2 pointings for each of the 3 fields, we achieve a cadence of 1 observation every 15 minutes, which is good enough to characterize super-Earths, given our short timescales for these planets of 1 to 2 hours. Then there's the next tier of observations occurs at 1 per hour, which is basically equivalent to a Neptune signal. And then there's a set of fields at 2.5 hour cadence and a set of fields at 5 hour cadence. And so these fields all nominally correspond to these typical planet masses, but actually the range and the duration of the signals is such that you may detect super Earths even in the lower cadence fields, depending on the exact properties of a given event. The KMT-Net group has a very large team working with it. In the top, I've shown the pictures of the science team, the members of the science team who are all working on the analysis of the data. And in addition to that, we're supported by a large operations team who run the telescopes and maintain the whole system and the data analysis pipeline. We also have funding from various sources. And so at the time that KMT-Net was commissioned, just before it was commissioned in 2014, there were a total of 30 known exoplanets. And they spanned a range of mass ratios. And so mass ratio is the primary observable for a microlensing planet. And so that's the mass of the planet divided by the mass of the star. And the x-axis here gives the log of that mass ratio. So a Jupiter would be at -3. Jupiter divided by the sun would be at -3 on this graph. And a key thing to note about these 30 planets is that there are very few objects below a mass ratio of 10 to the -4, which is where the dashed line is. And so what we will see is we will see that change with KMT-Net observations. So the first KMT-Net observations were taken in 2015, and the first planets were published in 2016. So now I am just showing planets from the KMT-Net project. In the top is the year, 2016 is the year of the publication, the number of planets that were published in that year, which is 2, and then on the right, the total number of planets published to date from the KMT-Net project. Then the legend gives the year that the observations were taken in which the planet was detected. And so in 2016, we published the first 2 planets from the 2015 season. In 2017, we add 4 planets, which were detected in 2016. In 2018, we add 13 more planets from the 3 previous seasons. They're distributed amongst the 3 previous seasons. In 2019, we have 11 more planets. In 2020, we actually managed to publish 19 planets from previous seasons, but the observations for that year were sort of a loss for pandemic reasons. But in 2021, things really start to change for KMT-Net, because at the beginning of 2021, Weicheng Zhang, who is currently a CFA fellow, he developed an algorithm to automatically and systematically detect planets in the KMT-Net data. And so because of this systematic search, we start a project to systematically analyze all of the new planet candidates from previous seasons. And so here we get a big jump. There are 21 planets that we publish in 2021, 48 in 2022, 39 in 2023, and as of the beginning of 2024, there were actually an additional 10 planets that were published, and probably more since I made these figures. So there are a couple things to note about this planet distribution. First, combining the KMT-Net planets with the previous planet detections, we're obviously at 200 or more detected planets with microlensing. And then we can see that from the 167 planets from the KMT-Net survey that have been published to date, there's quite a few of them that have mass ratios smaller than 10 to the -4. So we're getting about another decade worth of leverage on measuring the actual distribution of planets. In addition to that, you can see that there's sort of a feature. It kind of appears that there's a bimodal distribution of planets in this mass ratio distribution, with a peak around 10 to the -4 and one at sort of -2.5. But we're still in the process of doing the systematic sample. So we're working backwards through seasons and then trying to catch up to the present. And we're still in the process of really finishing out the complete sample, but we already, in parallel, are able to make a planet frequency measurement and a measurement of the mass ratio distribution by selecting a subset of the planets that have been actually systematically analyzed. And so we constructed this sample of planets. Above 10 to the minus 4, we take the planets from the 2018 to 2019 seasons. And below 10 to the minus 4, we use all of the planets from the 2016 through 2019 seasons. And so the light blue line here shows the raw detections of planet detections. And the blue line is corrected for the sensitivity function of KMTNet. And in particular, you can fit this with a power law. And so it just looks like a continually rising power law. However, there are several deficits in this power law. So first, there's a deficit at the high mass ratio end. There are fewer planet things above 10 to the minus 2. There's also a deficit in this bin between 10 to the minus 3 and 10 to the minus 3.5, which is what we might expect given the full distribution of all of the currently analyzed planets. And there's also a deficit of planets with mass ratios below 10 to the minus 5. So if we continue this power law, we sort of have an expected number of planet detections of 6 in the KMTNet sample, in this sample, but we only observe 1. And so there is a slight deficit at the very low mass ratio end here. And so even though you can fit this pretty well with a power law, you can fit it better with a double quadratic. And there's delta chi-square of about 22.6 between the power law and the double quadratic. And that's interesting because a bimodal planet distribution would be quite consistent with the predictions of planet formation theory, right? You might think that perhaps the lower mass ratio peak and the higher mass ratio peak would correspond to planets that have and have not undergone runaway gas accretion. And there would be a distinction between those two. Or you might say, well, if giant planets are formed by the gravitational instability mechanism, that would produce one population. And then the second population would be planets that are smaller and produced by some other different planet formation mechanism. And so this work has been submitted to Science and it's currently under review. I hope that it can become officially out in the world soon. But I would like to say that it's your move, planet formation theorists. In addition to the bound planet population, microlensing also detects free-floating planets. And free-floating planets have a similar set of considerations for detection as bound planets, right? The time scales as the Einstein ring, scales as the square root of the mass. And so free-floating planet time scales for the various smallest things are about an hour and somewhat longer for larger mass free-floating planets. And so with KMTNet, we started having a large number of planet detections that exhibit finite source effects. So this is an example of the light curve of a free-floating planet candidate. So its brightness as a function of time. And the time scale of this event is about 7.7 hours. And that allows you to measure the finite source effect here, allows you to measure the Einstein radius of 9 microarcseconds compared to, say, the 0.6 that we estimated previously. And so this is somewhat larger planet, but planetary in nature. And there are quite a few others in this category. But one thing that you might have noticed about that previous object and also about these objects is that their formal timescales of only, 1, 6, 7, 9 hours, that formal timescale is much shorter than the actual duration of the event. These events are actually typically lasting for a full day. And that's because what we're seeing is the finite source effect, which is basically the first to fourth contact of the source star as the planet transits in front of it. And so the observed durations of these events are actually set by the size of the source stars. And in this case, we're all dealing with giant sources. Okay, giant sources. And then So what we did was we actually carried out a systematic search of giant sources for events exhibiting finite source effects to construct a distribution of the Einstein radii, which remember is proportional to the square root of mass, from the KMT net sample. So this is a uniform sample of events. And there are a number of features. First, there's a cutoff at the high mass end. And that's just due to the fact that as the stellar population evolves, there are actually very few stars with masses greater than a solar mass. And then you also see a fall off in the stellar population towards brown dwarfs, that there are fewer brown dwarfs than M dwarfs. But then here we have our 4 objects with Einstein radii less than 10 microarc seconds, which strongly indicates that their masses are planetary in nature. But these 4 objects are also separated from the brown dwarf population by this Einstein desert, by a plateau, which suggests that they're actually a separate population of objects, such as free-floating planets, rather than being the tail of the stellar mass function. And so if you fit this with a power law, these events, this cumulative number distribution with a power law, then you find that a power law index of 0.6, which is what we see for bound planets, overpredicts the number of objects that you would expect in this Einstein desert, in this plateau. And so that suggests that the power law index for the free-floating planets is a lot steeper than what we see for bound planets. Recently, the MOA group also conducted a measurement of the free-floating planet distribution, and this time they used the Einstein radius and Einstein timescale distributions together to measure this FFP distribution. And what they find is their FFP power law index is very similar to what we find from Gould. So the FFP population here is the long dashed lines. But the stellar populations they find are slightly different. So Gould just, in the Gould paper, we just assumed a Chabrier mass function. But the Sumi paper fits a 3-part power law to their distribution. And they find that there are many more brown dwarfs than in Chabrier. But the key thing here is that regardless of what we're talking about, objects of super Jupiter masses are actually a mix of things from the high mass end of the free-floating planet population and the low mass end of the stellar population. And that suggests the possibility that there are a mix of objects that formed in a disk versus in just from direct collapse of a cloud. And so these proportions could be something that might be probed by planet formation theory and stellar star formation theory. And one caveat, though, with free-floating planets is that the definition of a free-floating planet in microlensing is one where you don't detect a microlensing signal from the host star, which means that the free-floating planets, that the things that we call free-floating planets or free-floating planet candidates could be real free-floating planets, or they could be planets in very wide orbits, such as Neptune, Kuiper Belt, or Oort cloud analogs. And actually, with any given planet, you have an either or, but when you're talking about the planet population as a whole, you're just talking about everything, wide orbit planets and free-floating planets together. And so this population of free-floating planets with this power law index of 0.9 or 1 is the population of just everything in wide orbits and that has been ejected from the solar system. So that's just something to keep in mind when you're thinking about trying to understand how this population relates to, say, planet formation theories. And so this is kind of the current state we're at. We have a good measurement of the planet mass ratio function for bound planets. And we also have this measurement of the free-floating planet population. And so what we see is that in 2015, we had about 30 planets. And then by 2024, we've really filled out this planet space detection space for brown planets. So where does that leave Roman, right? Well, this is the Roman sensitivity curve that was produced by Matthew Penny in his 2019 study. And then the cyan points are a simulated set of planet detections assuming a particular mass function. And so even though we've detected a lot of microlensing planets from the ground, there are still a lot of planets and a large part of planet parameter space that is uniquely probed by the Roman microlensing mission. In particular, the lowest mass planets and the widest orbit planets, and I include in that free-floating planets. And so as we're thinking about the Roman microlensing mission and what science we're going to get out of it, we're not just thinking, oh, we need to detect a bunch of planets. We're really thinking about what are these planets going to tell us, and how can we get the most science out of these unique parts of planet parameter space. And so I want to return again to the question of free-floating planets, because one of the things that is unique about Roman is that Roman is a lot deeper than goes a lot deeper than you can go from the ground. And as a result, the source stars are a lot smaller. And that means that the signals from these very small planet perturbations are less washed out, but they're also shorter time scale. And so Samson Johnson did a lot of work simulating Roman free-floating planet detections. And this is a table of his simulated detections given a fiducial mass function. And in particular, what we see is that the number of planets drops off significantly below about 1 Earth mass, but the cross-section is actually flat for the existence of those events, because the cross-section is set, as you get to increasingly smaller planets, your cross-section gets set by the size of your source and not the size of the Einstein ring or the mass of the planet. And the mass function he chose is also flat below 2 Earth masses. And so why are we seeing a decrease in the number of planet detections, even though the rate of such events and the mass function is constant? All right. And so if you look at the simulated planet light curves, what you find out is that the problem is not the signal to noise. The problem is the cadence, right? So you can see in these simulated light curves, there's plenty of signal to noise here.
3 minutes, Jennifer.
Thank you. But along the bottom, you see these dashed marks show individual observations at this 15-minute cadence. And the problem is that many of these are so short that you don't get very many observations during the actual event. And so 6 observations are required for a robust detection, but 3 are more typical when you do out the math. And so if you want 6 observations, you have a choice. You can increase your cadence, or you can restrict yourself to larger sources. There are fewer larger sources because of the mass function. Or you can restrict yourself to slower sources. Again, then you're restricting yourself to the tail of the mass function. And so when you combine these factors together, it turns out that when you have a cadence of only 4 observations per hour, you're limiting yourself to about only detecting 20% of the potential population of free-floating planets. But if you increase the cadence to 8 times per hour, then you get up to about 60, 63, 64, over 60% of the population that you can detect. And so this is a little chart that compares the cadence versus the fraction of the population you're observing, and then gives finally the net factor in the total number of net detections of small objects. And so even though, you get a factor of 3.4 by probing more of the population for this increased cadence of 8 per hour, but then you lose half your fields. And so the net factor of increase is 1.69. But there's some smushiness in this because you can actually get a few more planets if you increase the signal to noise.
1 minute.
Thank you. Okay, and so if you compare the original fiducial measurements, then what you get is you increase the small planet detections by this factor of 1.7, but you decrease the larger planet detections that don't benefit from because of the loss of the number of fields, and you just sort of redistribute your planet detections towards smaller masses. But, this calculation assumed that there are two, that the mass function is flat below about 2 Earth masses. But one might imagine that there are many more Plutos, or that the mass function rises for smaller objects, especially when you consider the ejections of things. And so the gains might be significantly more in terms of the number of detections of small objects, depending on what the true mass function is. And so these rough estimates still need to be verified by detailed simulations, right? These are fairly simple calculations, but they suggest that a higher cadence with fewer fields would be better for for the science, and for the more interesting parts of the scientific parameter space. And all the arguments that apply for free-floating planets also generally apply to smaller planets and wide orbit planets. But again, we are still in the process of verifying these estimates. And so I just want to close by returning to this diagram. This is where we're at now in terms of our planet detections. And these boxes are the places that I think are going to be the most scientifically interesting with WFIRST. And if there are any planet formation theorists who have predictions for what we would see in those boxed regions, I think that would be quite interesting. Okay, thank you very much.
All right, thanks, Jennifer. Questions in the audience? We can start from more junior folks if they have questions.
Hi, Jennifer. It's Dave Bennett. I had a quick comment on history. The first Roman-like, microlensing survey was actually proposed in 2001, and the KMTNet project sort of took form in the middle of the 2000s. We had a meeting in Heidelberg to discuss it in 2005, I think. And then my question. I recently visited J.P. Bellieu in Paris, and he showed me the light curve of what was thought in like 2001 is the first planet found by microlensing. It's Ogle 2000 bulge 26. But it turned out that this was a false positive due to a spotted Storch star. And then another event occurred in 2010. It was thought to be one of the first 20 planets found by microlensing was MOA 2010 bulge 523, which we all thought for a long time was a planetary event, but a co-author on the paper with initials JCY was rather suspicious and managed to show that this was actually a case of a high magnification event where the source crossed the lens crossed the stellar radius and was magnifying spots or something like that. And in the KMTNet analysis, I noticed that they're quite careful at considering false planets from binary sources, but I didn't see anything about considering false planets that might give these dips in the light curves. Some way to remove the false positives there. So I wanted to ask you about that.
As you noted, I know quite a lot about 523. The other one I don't remember quite. But I think that case was fairly rare. Because it's a very subtle signal at the peak of a high magnification event. And so most planetary signals tend to be more robust than that.
Well, okay, I wasn't entirely sure with some of your new low mass planet detection, so some of those signals are pretty subtle.
Hi, Jennifer. This is Alan Boss from Carnegie, one of the Eteretics who believes in disk instability. I wanted to address your challenge to theorists about filling in the boxes. I have a poster out here, which unfortunately you can't see, but claims that disk instability can quite nicely fill out the upper half of the upper right box. Can't fill out the bottom half of it or the lower left box, but certainly the upper right box is something disk instability could potentially fill up for you. Thank you.
Okay, thank you.
Okay, I'm going to take Chair's prerogative to ask the last question. I was quite curious, Jennifer, with your KMT net result with the mass ratio function, and you were arguing for potential bimodality and potential gap. And I was wondering how that shape might or might not change if you can get a better properties of the host star and get a mass function. And I ask this because in radial velocity surveys, we do not necessarily see a gap.
Yeah, so I think the prospects for the mass function, if we wait long enough, we should be able to detect light from the host stars and make a robust measurement of the masses for the existing KNT-net sample. But also with Roman, we should get masses for a significant fraction of the host stars. And so we should be able to do that there as well.
All right, let's thank Jennifer.